The desired signal comes from a certain direction and has some temporal statistics. And also the noise may come from different directions. And the model is that for each microphone or each sensor, sensor M from 1 to M, we write the signals as summations of xmt plus vmt. So this is the desired signal that is measured in the M sensor, and this is the additional, the additive noise. And we also assume that we have some relation between the desired signals that are received in each sensor and the source. So the source signal x t that propagates from a certain direction, so we can write that this part xm equals to xt, the original signal that was transmitted from the desired source, and it's convolved with a certain impulse response from the desired source to the sensor number M. And here, because we only focused on the enhancement to reduce the noise, we don't focus here, we don't deal with reverberation. So our objective is to estimate x1t, to estimate the desired signal in one of the sensors which we choose as the reference sensor. And we said that we need to choose wisely which one would be the reference sensor. For example, the one with the least amount of reverberation, or the one with the highest signal to noise ratio, something like that. This makes sense. Usually we take the sensor which is closest to the source, if it's in the near field. Otherwise, you can choose arbitrarily, okay, the reference sensor. And we said that when we work with multi-channel, we can estimate multiple samples at the same time, instead of one sample at a time. Of course, you can estimate one sample at a time. It's okay. But then the computational complexity is higher because you need to do it for each sample. There are some advantages if you want to reduce the complexity, and also you think this option is good for you, so we can estimate a vector of this signal. Okay, so we define a vector of this signal. So this is the estimate. This is a vector of the desired samples that are measured or that we have them in the reference sensor. Okay, so this is what we measure together with an additive noise, and we estimate. So this vector is an estimate of the desired signal in the reference sensor, and of course it includes all the reflections, reverberation. Okay, so maybe afterwards you want to do some de-reverberation if you can, or you can do an estimate of the original signal. So it's joint de-reverberation and noise reduction. So if you're interested in this method, you can just look for joint de-reverberation and noise reduction. You will get some methods. It's just like also with image processing, joint de-blurring and noise reduction. And other methods also. Other water acoustics also. You have some ways to do that, because over there it's even more important to deal with these impulse responses. Okay? So this vector is x1t, x1t minus 1, and so on. And generally, we can choose how many samples we choose. But let's take a vector of length L. So this vector, we can obtain it from some measurements that we get from the sensors and from all the sensors. So we combine L sensors from each, L samples from each sensor, and we concatenate them into a long vector of length ml. So we have a vector T of length ml by 1. So this is the vector. It contains L samples from each sensor concatenated over all the sensors. So here, what we try to get is to find a matrix, filtering matrix, and the size will be L by ml, which is multiplied with the vector T of length ml. So we combine. So all this is linear model and linear estimation. And then we defined also the performance measures. Okay, so performance measures, we talked about output SNR, input SNR, we talked about distortion, noise reduction, desired signal reduction factor, and we talked also about the mean squared error. So the mean squared error means, you see that when you estimate something like that, we have two components. One is because also here, this vector, we can write it as summation of two vectors of the desired signal. This is the desired signal that is measured in all the sensors, L samples, and concatenated over all the M sensors. So we have ML samples of X plus H ML samples of the noise. Of course, we don't know each one of them, but we assume that we know the correlation between any sample in this vector to any sample in this vector. So within the L samples, we know we can take any samples from any sensor and find the correlation to any sample with the same or any other sensor, which is a lot of information, and we call it Rx, and we know the same information also for the noise, RV. And we gave some examples. We gave some examples how to obtain these matrices. In practice, you need to estimate them. So if you read, for example, some papers, you can check my website, you can find the papers, and also about practical problems of, for example, speech enhancement and array processing, how to estimate something like that. Okay, and I hope that when you present your topics, you can talk about things that you're familiar with, what are the challenges, and so on. So you don't have reliable information, and you need to estimate. And then it's more challenging. Okay, so if we have this, we can define what is the mean squared error, for example, mean squared error. And we can define it as a function of H and try to find H that minimizes this mean squared error. In this matrix, we will call it a Wiener filtering matrix because it minimizes the mean squared error. But instead of working directly with the matrix H and these matrices, we said, let's transform the signals into the generalized, using the generalized eigenvectors of these two. Okay, so what we did, okay, I can write it here. So what we did, we said, let's find the generalized eigenvectors and generalized eigenvalues of these two matrices. So we know that these two matrices are symmetric, and also they are full rank. So we can find a matrix T and diagonal matrix lambda such that T transpose Rx T equals to lambda. Lambda and the diagonal contains the eigenvalues in a decreasing order, and the columns of T are the generalized eigenvectors, and also the same time T transpose RV T equals to identity matrix of size ML by ML. Okay? So we can find, we know how to find these matrix and these generalized eigenvalues. Once we found it, it's much easier to work with filtering matrices, to find optimal filtering matrices. So instead of writing J as a function of H, we can write H by A, T transpose. So now we formulate, instead of formulating the performance measures as a function of H, we can formulate them as a function of A in the transform domain, because T is known. And once we find the optimal A, we can find the optimal H simply by multiplying with T transpose. Okay? So if we find from the problem J as a function of A, we can find the derivative of this, a scalar function. We find the derivative, the gradient, with respect to the matrix A, equate it to 0, and find the optimal A that minimizes the mean squared error. And then we multiply it with the T transpose, and we get the Wiener filtering matrix. And it's easier to work also, as we will see, also to find the MVDR and other methods. And we saw that we can write, of course, you can write H, the Wiener filtering matrix. You obtain it in a certain way. You can write H, Wiener. So we saw that, let's see, okay. For the example. Okay, so you can write it directly without using this transform, this generalized eigenvalue decomposition. And you can find it like this. And also I gave you the definition of II. II is identity matrix, and all the other and below are 0. So you can check the definition. So we can write it as II, this is a matrix, multiply with Rx, Ry minus 1. Of course, we can obtain it like this. But if we use the transform domain and we find A, the optimal A that minimizes the MSE, and then we multiply with the matrix T transpose from the right, we get another formulation of the Wiener filtering matrices, which looks like that, which is a nice way to get this one. See, this one. So we got it as I Rx, summation from I equals to 1 to ML, and Ti, which is the column, the I column in the matrix T, Ti transpose divided by 1 plus lambda I. Lambda I is the ith element in this matrix lambda along the diagonal, which is the eigenvalue in a decreasing order. Okay, so this formulation is really nice because it enables us to take a smaller number in the summation here. We don't need to take all the elements in the summation. We can take smaller number. And also, another nice thing is that we don't need to compute the inverse of a large matrix. You see, this matrix is ML by ML. Here, we don't need to compute the inverse of this of a matrix. Sometimes it's helpful because it saves computational complexity. But of course, the computational complexity, we have it here with finding the transform. But here, so in addition to not, we don't need to find the inverse of a large matrix, and we write it here, it enables us to control the trade-off between signal distortion and noise reduction by changing the number, how many elements we sum in this expression. And then we said that if we reduce, so here we, instead of taking the summation overall until ML, we can take some summation with a smaller number, let's say Q. So we call it a different filtering matrix, which we call it variable span. Okay? So we call it variable span Wiener filtering. Okay, all this I can delete. So from this expression, we found an alternative way to do, to add some, you see, with the Wiener filtering matrix, we don't have a trade-off to control the signal distortion and the noise reduction. We don't have, because we just minimize the mean squared error. So this minimizes the mean squared error. But if we define another matrix that with a parameter Q that looks like that, summation from I equals to 1 to Q, and Q is generally smaller than ML, then we can control the trade-off between noise reduction and signal distortion. Which is nice. And then we saw also an example how the choice of Q controls this trade-off. And you see, when we talk about trade-off between noise reduction and signal distortion, we always want to do it in a smart way. We don't suppress more noise if we want to suppress noise. First, we put to 0 all the noise components in the noise subspace. Okay? This is obvious, because then we don't pay for that. We don't pay for that with signal distortion. So always, when we have a signal subspace, we have a signal subspace, okay, and noise subspace, we remove all the components in the noise-only subspace. This is first thing with all filters, whatever you do. Now, in the signal plus noise subspace, we want to reduce noise. Of course, it will come with a cost of increasing the signal distortion. And the smart way is to reduce in such a way that you pay the least amount of distortion for noise reduction. So you want to reduce maximum noise with the least amount of distortion. And the nice thing is, okay, nice thing is that when you increase I, and you, okay, we need to prove it, okay, but I will talk about it, how to think about it. When you see a summation here, so the first term reserves the maximum amount of signal. The second term is the second, and so on. So if we remove the last term, it reduces noise with the least amount of distortion, and so on. So gradually, we remove the last terms, which is not obvious in this formulation. Why we can take that? Why do I have that? And you need to prove it. I didn't prove it here, but I want you to understand that when we find the generalized eigenvectors and generalized eigenvalues along the diagonal here, so lambda I is in a decreasing order, okay? And what I claim is that once you order the generalized eigenvector, generalized eigenvalues in a decreasing orders of lambda, the first term and the second term and the third term, so it goes like the significance of the last terms are less important than the first terms. So it's in a decreasing order of importance regarding the signal distortion. So once we remove the last terms here, we're able to suppress noise with the least amount of signal distortion. Okay? So we want to show, we can show that when we increase Q, Q to Q plus 1, we have less distortion. Okay? That's why we want to remove the last terms when we want to reduce. Of course, you could ask why to start from I1 to ML. Maybe we can start from the second, from the third, so on. But this doesn't make sense, because then when you reduce noise, you want to produce the least amount of distortion. So when I talk or mention or try to find something, a variable, like here, a variable Q, that will give me a control between signal distortion and noise reduction, I need to do it in a smart way, such that I get the maximum amount of noise reduction with the least amount of distortion. Otherwise, this variable is not a good way to control this trade-off. When I talk about trade-off, I mean optimal way to control the trade-off. This is important. Just like we mentioned that in the single channel signal enhancement, in the time domain, in the frequency domain, when we add mu over there with the trade-off, so that was a way to do it, and so on. So you need, when you provide some variables to control something, here in our problem is to control distortion and noise reduction. But if you, in your research, you try to control some trade-off, you need to prove that this is the best way to control the trade-off using a certain formulation. I don't say that this is the only way to control the trade-off. Of course not. We will see other ways to control the trade-offs. But once you use a certain parameter, you see, maybe I need to choose the first one, the fifth one, and the element number 19. Maybe it's better than choosing, suppose that I want to choose 5 elements of this summation, only 5 elements out of ML elements. So what I say, using this formulation in this generalized eigenvalue decomposition, I tell you, if you want to take summation of only 5 elements, take the first 5. And you need to prove that the first 5 are better than taking any other 5 elements. Okay? Any questions so far? Okay, so we talked about the variable span Wiener filtering matrix. We also showed some examples, and we saw that if we take the first element, actually, it generates a way to maximize the output SNR. So if we take only the first element, which looks like that, T1, okay? So if we take only the first element in this summation, we get a filtering matrix that obtains maximum output SNR. And of course, we have other solutions to obtain other filtering matrices to obtain the maximum SNR. So we can put number 1. So this is one of the options, like this, which is nice. You see? So from this formulation, we obtained also variable span, so we can control the trade-off between signal distortion and noise reduction. And we can also get easily, by taking only the first term, filtering matrix that maximizes the signal to noise ratio. And we can show also, we can prove mathematically that this filtering matrix, it maximizes the SNR together with minimizing the mean squared error. So if we take out of all the filtering matrices that maximize the output signal to noise ratio, and we want out of all these filtering matrices to find the one that minimizes the mean squared error, it will be this one. And it was obtained from the first term in the sum of the Wiener filtering matrix. By the way, I gave you, shared with you the book chapters. At the end of each chapter, there are many problems. So if you like, if you have more time and you want to prove everything, so you can prove, you can just follow the problems at the end of each chapter and try to prove things. So it's a good exercise. So many things that I say, I don't give you the proof, but you can prove it, so it's in the book. Okay? Any questions? Okay, good. Now we can move on to the MVDR. Okay, so the MVDR, what does it do? The MVDR, if we go to this transform domain, we know that the components of the signal are spanned by some P eigenvectors, generalized eigenvectors, because the dimension of Rx, the rank of Rx is P. Smaller is a lower rank. So if we keep these eigenvectors, the projection on this signal subspace, we don't touch it. We don't reduce any noise in the noise plus noise subspace. We remove only the noise in the noise only subspace. We get MVDR. It's very nice. So how do we do it mathematically? Once we do it in the transform domain, it's much easier because we can separate. We can have an optimal separation between the signal subspace and the noise subspace. What does it mean, optimal separation, it means that the signal or the dimension of the noise-only subspace is the largest. Because we have the least number of eigenvectors or basis functions that span the signal subspace. So the signal subspace is the most concentrated in that transform. Once we have such a transform that we can concentrate all the signal components into the smaller dimension of the subspace, we can have good separation between them, and then the MVDR will be able to suppress as much as possible noise without any distortion to the desired signal. Okay? Makes sense. That's why we work in this transform domain. You can ask, is there any other transform? But we can show that this is the optimal. Sometimes we don't work with such kind of transform because it's expensive. It's expensive computationally to find these generalized eigenvectors and generalized eigenvalues. But then you can do something which approximate or come closer. For example, with speech, you can choose the short-time Fourier transform. With images, you can do something else. Sometimes we work with the two-dimensional DCT and so on. But then you can do offline some computation, and you can ask how much performance we lose because we didn't use the optimal subspace transform, the optimal transform like this, and we used an approximate alternative transform like the STFT or the 2D DCT for images or some other transform. And we want to know how much we lose, how much the performance degrades. This is a good question, and we can test it on real signals. Okay? So if we don't adapt the transform to the signals, we can obtain lower computational complexity, which is very important. And then we can compare it to the best transform and see how much we lose in terms of performance. So for the MVDR, we need to find the optimal A such that we get maximum noise reduction without any distortion. So how do we do that? We need to find the matrix A such that when we apply, so I delete it over there, but we need to show that when we apply H, which is A, T, T transpose, okay? When we apply H to X, okay? If we apply, this is the filter desired. This is a vector of ML by 1, okay? This is ML by 1. This is the filtering matrix, which is L by ML. So we need to show that this is the filter desired signal. We need to show that this will be X1, which is L by 1. This will obtain or will generate the first L samples or the L samples in the reference sensor. If we have this, do you agree that we have distortionless response? Yes, good. Because Z, okay, I need to add here T, just notation. Because ZT, which is an estimate of X1, is HY. So if we apply H to X, Y is so if we apply H to X, we want to get exactly the original signal without any distortion. of course, we will pay for that by removing less noise. But so we remove only the noise in the noise-only space. So if we write it like this, we can write it also in the transform domain using the matrix A. Because H is A T transpose. So in the transform domain, we work with the matrix, the filtering matrix A in the transform domain, and we show that this requirement, the distortionless requirement, is the same as this. You see? A lambda is II Rx T. And you could put, you can first, there are different ways to find it. Either you find it from here, or you take the MSC that is based on the distortion MSC, distortion-based MSC, JDA. You minimize it, and so you find the gradient of this and equate it to 0, you find this. And once you use it, you need to show that actually the MSC of the distortion will be 0. But you can also find it from here. Okay, so you can practice, try to solve it. And from here, because lambda is diagonal, lambda contains the generalized eigenvalue. So it's very easy to invert it like this. But you know that lambda contains p eigenvalues, which are larger than 0, and the others are 0. So you cannot just take lambda minus 1, it's non-diagonal. But if you take a diagonal matrix with some 0 elements, it's very easy to invert it. We call it pseudo-inverse. Okay? So pseudo-inverse, it means that you take the inverse in the diagonal of the non-zero elements, and you keep the 0 elements in the same place without touching them. Sometimes, even the small eigenvalues, you see, the small eigenvalues, sometimes we put them to 0 because this becomes large value, but this will create some distortion. So here we take all the non-negative eigenvalues, we invert them, and this is a pseudo-inverse of diagonal matrix, which is very easy to do. See? So this is the matrix of the MVDR. If we multiply with T transform, we get the MVDR filtering matrix, which looks like that. So here we get a nice formulation for the MVDR, which looks like, you see, also we have summation. But instead of 1 plus lambda, what do we have here? Lambda. So first, it's very nice to see the equivalence between here, this expression, and the Wiener filtering matrix. Two differences. First, here, instead of 1 plus lambda, we have lambda. It's okay? The second thing is that summation goes to P. We don't need to go to ML, only to P. So we take this summation only over the first P elements of the generalized eigenvectors and the generalized eigenvalues. So this expression gives us exactly distortionless response. So the desired signal is undistorted, and we suppress all the elements that contribute to noise in the estimate. We remove all the noise in the noise-only subspace. So let's write it. HMVDR. So it's IRX summation I from 1 to P Ti transpose divided by lambda. Now we can ask ourselves, we have an expression for the MVDR. Now suppose that we want to enable some distortion in order to reduce more noise. The MVDR reduces the maximum of noise without any distortion. Now suppose that I want to reduce more noise, additional noise, and to pay with some distortion. But I want to pay with the least amount of distortion. Which element out of this summation I will get rid of? The first one, the second one, third, or the last one? Okay? The last one, okay? So because the eigenvalues, the generalized eigenvalues, are ordered in our transform by decreasing order, so the last one, if I remove the last one, the distortion will be minimal. And then, so these elements are ordered according to decreasing order of distortion. What will they create if I remove them? So if I want to remove some amount of noise with the least amount of distortion, I will take this summation from I equals to 1 to P prime, and P prime can be smaller than P. Ti transpose lambda I. Very nice. So we have another way to control between speech distortion and noise reduction using this parameter, P prime. So we can call this something. You can choose a name, okay? But we can choose a name, so we can call it H control distortion, okay? But any name is fine with the parameter P prime. So this filtering matrix enables us to control in a smart way between noise reduction and speech distortion or signal distortion by using a parameter. And you see, it's in a smart way because it's easy to control using the parameter. We just take the summation until some components, because these components are ordered in the best way according to decreasing order of the trade-off between noise reduction and signal distortion. It's beautiful, you see, because sometimes you think, okay, suppose that I need to remove some components, I need to find it. Here you don't need to find. It's already in order of importance. Also here, it's in the order of importance that allows us to do some smart control over the trade-off. Now, if I choose only the first component, it means that it will keep only one component of the signal in the best way, where the signal is the most concentrated in that component. And actually, it will reduce also maximum SNR. I can show that even the first component, if I use it, I get maximum SNR filtering matrix. How do I know that? Because if I use it, the output SNR will be the maximum possible value, lambda 1. Okay? So you see, this is another expression for maximum SNR filtering matrix. So I call it number 2 because it's another expression. I want to identify this from this. Both of them, if you use them, the output SNR will be the maximum possible SNR. What about, so what is the difference between these two? If I have two different expressions that produce the maximum SNR, okay? What's the difference? So I said, sometimes I have an infinite number of filtering matrices that can generate the maximum SNR. So here it's the filtering matrix that produces the maximum SNR, but out of all the filtering matrices that obtain the maximum output SNR, I choose the one that minimizes the MSE. Here, out of all the matrices that obtain the maximum SNR, I choose the one with the minimum distortion, minimum signal distortion, which is different. Okay? Minimum distortion is this part becomes as close as possible to X1. What is MSE? That this part is as close as possible to X1 in the mean squared error sense. It's different. Okay? So we have here different expressions out of the infinite number of filtering matrices that obtain the maximum SNR. We have specific solutions that we got immediately from these expressions. You see the beauty of these derivations, and it allows us to do some more ways to control between signal distortion and noise reduction. You see, so if we have here a way to control between noise reduction and signal distortion, and here I have a way to control between signal distortion and noise reduction, which one is better? Which one is better way to control this trade-off? Okay? Is it a legitimate question? Always when you do research, ask questions, even if you don't know the answers. Research is to answer the questions, but the significant part of research is to ask questions. When you get something, ask questions. Be curious about what you get. Okay, so what do you think? Give me any answer. Intuitive, not intuitive, or think about an answer. Can be correct, incorrect, everything is good. What do you think? So which expression is a better way to control between noise reduction and signal distortion? Which expression is better? What? This one is better? The CD, the control distortion, is better than this one? Okay. Somebody think differently? Okay. So I think I gave you a clue when we talked about this. So I'll go backwards. Ask which one, this generates or obtains the maximum SNR. This obtains the maximum possible output SNR. Both obtain the maximum SNR. Which one is better? This one or this one? Both obtain the maximum SNR. Which one is better? If we have two expressions, two things that produce the same results in terms of output SNR, so what are the differences between them? What are the differences between these two? Both produce the maximum SNR. What are the differences? Exactly. Exactly. One minimizes the mean squared error. One minimizes the distortion. Okay? So it means minimizing the MSE, it means that the difference between Z and X1 on the average, it will be minimal using this. But if I care only about the signal distortion, the error between this part and X1, it will be minimal using this. Okay? So I can ask more questions, but I don't want to add more questions. One question at a time. So which one is better? MSE or distortion? MSE is better than distortion? Okay. And also you think MSE or distortion? Distortion. You see? So two people think differently. But you are both right. Because it depends what you need. Because in some applications, the distortion is more important. So you will choose something that minimizes the distortion. In some applications, you don't care about distortion, you care about the error, the mean squared error. Okay? And then this expression is better. So with the maximum SNR filters, also in the time domain, frequency domain, what we showed in the time domain, also here in the multi-channel, maximum SNR. So you have many solutions. So you have a degree of freedom to choose which one you choose. So if you care more about the MSE, you will choose this. If you care more about distortion, you will choose this. So it's a flexible. See? Okay. And another question. Which one suppress more noise? Which one? This one? MSE? Number one or number two? Both generate the maximum output SNR. Okay? One of them minimizes the MSE out of these matrices. One of them minimizes the distortion, this part. Second one or first one? First one. Okay? Okay, why? Makes sense. Okay? I agree. Makes sense. The first one, the MSE, it minimizes the difference between this and X1, the MSE. So it's MSE-based maximum SNR filtering. So it means that it gives some importance or weight to both this and this, how they different from X1. So the residual noise is also important. Here, we care only on the distortion. So we want this to be as close as possible to X1, which means that we don't give any importance to the residual noise. So it will try, so this filtering matrix tries to minimize the error between the filter desired and X1, but it will pay. We'll pay for that by increasing the residual noise. Okay? So the part of the residual noise will be higher in using this compared to using Hmax-Y. Okay? So we have nice expressions, and then we can ask some questions and so on. We can continue with that. So you see, it's very beautiful when we work with some expressions, and we can also think. So when you take summation, you also get nice order of their importance. If you work in a with a different transform, it's not that obvious. But you can approximate, and you can try to find which elements to remove. But when we work with eigenvalue decomposition, just like we work with the time domain, or when in the multi-channel time domain we work with generalized eigenvalue decomposition, it gives us beautiful expressions that we can work very nicely and derive different filters in a straightforward way. Okay? But we need to understand what we get, because sometimes we get the mathematical expressions and we don't know how to interpret them. So it's important that we know how to handle them. Okay, so this is the MVDR. So actually what we got now is 3 more filtering matrices. MVDR, control distortion, and filter that maximizes the SNR, maximum SNR filtering matrix that minimizes the distortion. Very nice. So actually everything I already explained, so I can skip. I can skip the derivations. And the nice thing is that also the output SNR with MVDR is always larger than the input SNR. Okay? So even that you take all these components, you see the maximum SNR is obtained with the first component. With the first component. If you take P prime smaller and smaller and smaller, you increase the output SNR. So you increase the output SNR, you reduce more noise, but also you increase the noise reduction, you increase distortion. Okay? But even if you take all these components, of course, the output SNR is at least as the input SNR. When do we have equality? What do you think? When using this? When what? Rx is full rank, which means that P equals to ML. Very good answer. Good, good. Because then we don't have noise subspace. It's empty. We have only signal plus noise, so we cannot remove any noise using the MVDR if we don't have a noise-only subspace. Okay. The control distortion is taking the summation up to P prime, which is smaller than P. Okay, and then we can control and so on. Let's see an example. So, by the way, you told them that we continue until 10:30, okay? So we continue instead of 1 hour until 10:30 because today is Christmas, so the break will be at 10:30, okay? So I don't want them to rush and think, okay, well, maybe I forgot about the break. Don't worry, I'll give you a break at 10:30. Okay, so let's see an example. If we return to example number 2 that we talked before, actually, if I go back to the example, so it was yesterday, so maybe you don't remember. So this is the example, that we have a signal like this, xt prime. So we have a signal that we don't know the properties of the signal, but we know the correlation between any two samples in this signal. Actually, we have some signals like this, that the correlation between two samples decays by their distance, the distance between samples. The more distant they are, the correlation decreases. And alpha doesn't have to be a positive number. So sometimes we have correlation which is negative, which means that the sample changes sign from one sample to another. So the odd samples can be negative, the positive samples can be positive, but we have some correlation between the samples. So alpha can be even negative. But it has to be smaller than 1, so the correlation decreases. Okay? And we can find for this example, suppose that we have the signal, the desired signal that comes from, let's say in the example 2, I think it's over there from the broadside. And in this area, okay. And interference, and we have also thermal noise, and the interference comes from the end fire. So we can find the correlation matrix and correlation matrices of the desired signal, Rx, and the correlation matrix of the noise. And suppose that here we choose alpha to be 0.8, and we take L samples, 10 samples for each sensor, from each sensor, and we have 5 sensors. Okay? So this is the example that we showed with the variable span, and if we take the controlled distortion, so we have also some trade-off with the controlled distortion. You see, so if we compare the controlled distortion, first I want to describe what we get with the controlled distortion for the same example that we showed also before for the variable span. So with the variable span we changed Q. With the controlled distortion we change P prime. So P prime can be 1, 2, 3, or 4. Okay? 1, 2, 3, or 4. Okay? So when we take P prime to be larger, so we add here, we have here more components, so we reduce less noise. So the noise reduction factor decreases, and the signal to noise output SNR decreases. You see the maximum SNR is obtained with P equals to 1. And when the noise reduction decreases, also the distortion decreases. See, so by controlling P, we can control the trade-off between noise reduction and signal distortion. And the MSC also decreases when we increase P prime. So if we compare the MSC, you see, if we, okay, well, first question. If I compare here the output SNR here that is obtained with P equals to 1, or the output SNR that is obtained with Q equals to 1, which one will be higher here? Same example. If I compare the output, the gain in SNR as a function of input SNR, one for using the control distortion filtering matrix with P prime equals to 1, compared to the variable span that we had here, variable span, which is here, with Q equals to 1. Which one will generate higher gain in SNR? Okay, simple question. What? Q equals to 1? Let's compare. Let's compare. So here, the value here, 24.3 approximately. Let's go to the previous one with the variable span. Here. This is, let me see if it's the same. Okay, so alpha equals to 0.8, and L equals to 10, and M equals to 5. Let me check that the input SNR, so So it depends also on the input SNR. As a function of the input SNR. Okay? So if you compare, so here it's 24.3 approximately. Over here, the same as the same range of input SNR from -5 to 15 dB. 24.3 approximately. So it's hard to see, but so it looks similar, but it should be the same, right? So it's the same. Of course it's the same. So that was an easy question. Why is it the same? Exactly. So H max 1 and H max 2 both produce the same output SNR, the maximum SNR, lambda 1. So of course it's the same. But now let's compare the MSC. Which one produces lower MSC? Using the first one, this one or this one? Which one produces? The first one. Okay, so let's check, because maybe something is wrong with the simulation. Okay, so let's check. So here the MSC is about 9.5, slightly below 9.5. This is using the variable span. Okay, which is the first one, 9.5. Let's go to the controlled. So the MSC is here. Okay, so maybe it's almost the same, but this is the first one. Okay, so maybe the difference is so small that we don't see it. Okay, if we go further, but if we increase P prime to 4, for example, so we get this value using 4 terms. So it's about 7 point, this is 8, so let's say 7.7. If we go to the previous one, see here, so it's 7 here with a variable span, Wiener. Okay, so it's much lower, because with a variable span, we try to minimize the MSC. So if we take 4 components, actually here it's 9 components, so it's unfair. So here with the Q equals to 5, this is 5. So this is with 5 components. So we need to compare the same number of components, okay? So it's more fair. So let's take Q equals to 2 here. So it's 8.75 maybe, 8.75. Well, maybe it will be similar. 8.75. So the MSC is quite similar. So you see in this example, it doesn't, even though here we try to minimize the MSC and here we try to minimize the distortion, the differences in terms of distortion with a small number of components is not necessarily big, okay? So maybe small differences. For this example, you see, because the distortion is, and so probably the noise reduction will be also something similar. But this is a different way to control how we control the distortion. Okay. Now let's talk about additional way to control distortion, which we are familiar with. When we try to minimize, we obtain the Wiener filtering matrix by minimizing the MSC. And we know that the MSC, J, A, the MSC, is composed of two components. One is related to the distortion, and one is related to the residual noise. So instead of minimizing their summation, we can put here a parameter, mu. So if mu, larger than 1, we will have more noise reduction. And if mu is smaller than 1 compared to the Wiener filtering matrix, if mu is smaller than 1, we can have less noise reduction and less distortion. So it's also something that we are familiar because we studied that. This is a nice way, also an alternative way to control. So let's see how it looks like. So the trade-off filtering matrix, see, we try to minimize using a Lagrange multiplier, and we get this formula. So using this formula, how does it compare to the Wiener filtering matrix? Simply, instead of 1, we have here mu. So this is H, the trade-off filtering matrix. Okay? So this is trade-off filtering matrix, which is I, Rx, summation from I equals to 1 to ML Ti transpose divided by mu plus lambda I. So we say, okay, why should we control the trade-off between noise reduction and signal distortion using one parameter? Maybe we can choose both mu and also here Q. Okay? This is one question. So we can control using two parameters. Why to limit ourselves to a single parameter? Another thing is, what happens if I put here mu equals to 0? What does it mean? If mu equals to 0 and I try to minimize this, so I don't care about noise. I care about distortion. What do I get if mu equals to 0? MVDR. MVDR. And if I reduce the number of components, I get the control distortion. So all these connect. You see the relations between all these filtering methods. They're all connected when you have a combined representation of these filtering matrices. So what I can do, I can formulate, I'll return to this example shortly, but I now can formulate a more general filtering matrix. I will call it general subspace filtering matrix. It's just a name. You can call it any name. You give it an Indian name. Okay? It's also fine. Any name is fine. Makes sense. You can invent names for new things. Try to do it for new things. If you do it for something which is known, and you put a new name, so people think, okay, you're not familiar with what exists. You know, sometimes people find a star, a new star, and then they give it a name. Some people look for stars. They spend many hours to look for a star that was not named before, so they can give it a name. You know? So you can also do it in mathematics and signal processing. Okay, so suppose that you have this filtering matrix. You see we have two parameters, mu and q, that control the trade-off between noise reduction and signal distortion. A very beautiful way to control the signal. But now we understand something which is very nice. We understand that if we take mu equal to 0, if mu is 0, we get a control by minimizing the distortion. We put more emphasis because if we put mu equals to 0, we put more emphasis on the distortion. So we have control under the constraint or under the additional requirement of minimum signal distortion. If mu is larger than 1, so mu is larger than 0. Okay, so it can be 0 or larger than 0. If we take mu, we increase mu, we give more emphasis here. So as we increase mu, we reduce more noise. And still, for a given mu, we can control the trade-off between noise reduction and signal distortion by choosing Q, which is smaller than ML. But if mu equals to 0, don't put here something which is larger than the dimension of the Rx. Okay, so the maximum Q can be P. Okay, so we write here Q between 1 and ML, but if this is for mu larger than 0. If mu is 0, the maximum value of Q will be P. And you understand why. Because we gone through all of that. So we have many special cases of this general formulation. So we obtained a nice way to control signal distortion and noise reduction using two parameters, mu and Q. And we also understand each one what it does. So this we explored. Let's go to the example that we skipped with the trade-off. Just a minute. Okay, so this is the example. So we have the same example. So I just want to show the effect of mu. So here we have the gain in SNR, we have the MSE, we have the noise reduction factor, and the distortion, the desired signal reduction factor. For different values as a function of input SNR, for different values of mu. So you see, let's see here, the blue line is with mu equals to 0.5, the green mu equals to 1, red mu equals to 2, and then the last one, the light blue, cyan, is mu equals to 5. So you see for a given input SNR, when you increase mu, the noise reduction factor increases because we suppress more noise. We increase mu, we give more importance to this part, so the noise reduction increases. And then the output SNR increases because we increase the noise reduction. And the distortion also increases because we pay for that with the signal distortion. Here, the minimal MSE will be obtained when mu equals to 1, because mu equals to 1 minimizes the total mean squared error. That's why the green line obtains the minimal MSE. Any questions? Okay. So this is a nice way we derived it. And here you have a very table that shows. So this is the general subspace with the parameters mu and Q. And all the others can be considered as special cases of this general formulation. Okay, the Wiener, variable span Wiener, MVDR, control distortion, maximum SNR. So we have two options. Okay, but we have actually more than two options. Any mu that we put here, so I showed here mu equals to 1 and here mu equals to 0. But actually, any mu will generate the maximum SNR. Okay, so you can choose any mu. How to choose mu? So actually, this expression gives you the maximum SNR filtering matrix. So we have, you see, you have an infinite number of filtering matrices that generate the maximum SNR. And then we can choose mu such that it will control the trade-off between noise reduction and signal distortion. Intuitively, think about, we have many signal components in the signal plus noise subspace. So with the maximum SNR filtering, we keep only one component. Which component do we choose? The one with the maximum SNR, okay? Exactly. So we keep that one. Now, if we multiply this component with a certain value, do we change the output SNR? No. We don't change the output SNR. Okay, so we multiply this component with any value. But we change, if we multiply it with a certain value, we change the MSC, we change the distortion, and we change the noise reduction, okay? So we can control what is the value that we multiply this component. Still we get the maximum SNR, but this variable that we change, we multiply this component, will allow us the trade-off between noise reduction. So even with the maximum SNR, we can control the trade-off. So this is a way to choose the component with the highest SNR, and then we control how much we reduce noise compared to how much we introduce distortion in this component. Okay? And we have the trade-off, more general, that we choose more elements. This is the general form. Any questions? Okay, so you have here some references. And now is exactly the time, almost 10:30. So I'll give you a break, and then we will continue. Now that you understand the single channel in the time domain, you saw that when we move to multi-channel in the time domain, it's such an extension of the problem formulation, the derivation, and so on. And we did some extension that was really nice. We found that the filtering matrices take into account the temporal correlation and also the spatial correlation in the vectors. So now, in the frequency domain, in the single channel, we used only gains for each frequency. We worked with each frequency independently, and we found the optimal gains. Now, when we go to or extend it to multi-channel signal enhancement in the frequency domain, we now will use the correlation between sensors in the frequencies. Okay, so if we have two different sensors, we will use the correlation between the frequency components of these two sensors. So we are able to do also spatial filtering in addition to filtering in the frequency domain. Okay? Questions? Okay.